Okay, stack. Now this is, of course, a fundamental data structure in programming, just about any language, right? Even in high-level language C, you still have a stack, right? Because you have to call, return. How does it manage the return value, or how does it manage local variables? Well, the answer on the stack. Well, Java does it differently in that Java does dynamic memory allocation, so its local variables are allocated in the heap as opposed to stack. But that means it pays the price of garbage collection. Whereas C, if you use just stack allocation, then by the time you return, all the locals are gone, right? Now, 8051 hardware supports stack in its iData memory space. And these instructions are push and pop. Each one takes a direct address as its operand. And also there is a stack pointer, or SP, that's a special function register, that gets incremented or decremented as a result of doing a push or pop. Okay, so push, of course, means adding an element to the stack. Pop means removing the element from the stack. Now, so on power up, 8051 hardware initializes the stack pointer to the iData address 7. And you say, hey, that's the register R7 of bank 0, right? Is that a good idea? Well, turns out 8051 stack works a little differently from everything else. If you have taken C or most other architecture, the stacks grow downward. That is, they start from high address. When you push, it goes to a lower address. And when you pop, it goes back to higher address. Right? So, because it's on the opposite end as your heap memory or globals and all that. Right? Chances are you don't want the two to collide. Now, 8051 with the hardware supported stack grows upward. That is from lower address to a higher address as it gets pushed. And when you pop, it goes down to lower address. So even though it's initialized to 7, when you push, it increments it to 8 first, and then writes the data byte at 8. So this way, it will not trash your R7 of bank 0. But you say, hey, but what if I'm using bank 1? Well, sorry, it's overlapping your bank 1. So that's not a good idea. So by default, you're using bank 0. You're not using bank 1, 2, 3. Those are really for your stack. But what happens a lot is a compiler or even assembler is going to say, let me estimate how much stack space I want to use. And then so first thing it does is sets the stack pointer to something, usually like a 30 or 80 or something. So that way you get to use your register bank, different banks, or you can allocate memory with better control. Push is pre-increment, so it increments or adds 1 to the stack pointer first before it writes the value. So that way, it's always pointing at the top of the stack. Okay, so if you dereference SP, you get the element there. Pop is post decrement, so it removes it reads the element out and then it decrements. Okay, so that's 8051 hardware supported stack works. If you have to do your own software stack, well, you can do whatever you want. Doesn't really matter. But this is at least hardware supported. So that means the stack pointer is manipulated by push, pop, and a few other like call, return instructions. Now the syntax looks like this, like push and then some direct address. So you say push 6. If you're not careful, you say, push the value 6 on the stack, right? No. It's direct address 6. Why? Because there's no pound sign in front. Right? Pound sign says, okay, push value. But 8051 does not allow you to push an immediate on the stack. the only format it allows is a direct address. So push must take a direct address. So what if you want to push a value? Well, sorry, you have to do a move of a constant value to that address and then do a push of that address. Okay, that's the only way to do it. In fact, you can't even push A. You can push, well, A is the accumulator. You can't say push A, but you could say push ACC. Why is that? Well, ACC is the direct address form of the accumulator. So it's explicitly addressing A, okay, as opposed to implicitly addressing it. Okay, anyway, so push 6 means push the content at IData address 6 to the top of the stack. And if you're selecting bank 0, then that happens to be register R6. Pop 2, again, that 2 refers to the address. So you're removing the top of stack content, put it at the address 2 in IData space. Okay? So that's something to be careful with for the push and pop. So value for stack pointer. So if you don't do anything, it goes from the range 7 to 1F. Now, sure, it could actually keep going up, but usually that's not a good idea because hex 20 and up, that is a special region called bit addressable region, and that's usually reserved for something else, and you should avoid that. So for simple little things, you don't have to do anything to the stack pointer. But a lot of compilers, just to be conservative, they say, okay, let me move it up to hex 30 and up, just so I avoid the parts I shouldn't touch. So that's what a lot of compilers do, actually, in the initialization part. Now on 8052, which is a little extension to 8051, and that's in fact what virtually all the 8051 compatible microcontrollers are today. Even though they say 8051, they're actually 8052. There's actually an extra region of memory from 80 hex up to FF. And that is another popular area for using the stack. Okay, and we'll talk about that part later. Now, stack is used also by what's called call and return instructions. Now, in 8051, there's something called ACALL and LCALL. ACALL is for absolute call, and LCALL is for, I think, what is it called? Long? I forgot. But, well, it doesn't matter. So one of them is 2 bytes, one of them 3 bytes. I think ACALL is more limited in that it's only within a 2-byte space, 2K space. LCALL I think can go entire 64K space. Now return is the return instruction. It must be paired up with a call. So what call does is it's like a jump to a destination address, except it also pushes its return address on the stack. On which stack? Well, the IData one. Okay, so it actually changes the SP. By adding 2 extra bytes onto the stack. Okay, so this allows you to have nested calls, right? So you can call one subroutine, which then calls some other subroutine that just keeps pushing. And when you return, the last one that was called is returned first. So it pops off, right? That's what return does. Okay, and so so return is paired up with one of the call. Could be ACALL, could be LCALL. It really doesn't matter. Now, the stack is also used during interrupts. You've heard of interrupts, right? It's when you have some timing or some transition event. It could be, or if you have serial port that receives a byte of data, right? You can set it up to interrupt you. So interrupts actually use the stack as well. But to return from an interrupt, you have to use RETI, return from interrupt, as opposed to RET. Why? Because an interrupt actually does something different, saves a lot of different states. So it's not a subroutine call. But again, it uses the stack as well.